Thank you very much for the invitation. I'm very happy to be here to explain some things which have been in collaboration with Group in Kaust, with Raoul Temponen, Erik von Schwerin, and Akko Kammonen. So the title is Generalization Error for Random Features, and I will try to present simple proof for that. First comes the setup. So we are given data with xj and yj. They are xj are in RD and yj are in R, and we have j data points. And we assume that the data are related by yj is a given function plus some noise. The noise will have expected value 0 and finite variance. And the data points xj, they are IID samples independent from the noise. That this is the common setup. Now, we assume that we have a representation of the function that we want to approximate, so that we can write the function as a kind of amplitude and a neural network activation function like this. And we include the bias by adding the 1 here. So for instance, if we would use the trigonometric activation functions, we could use the Fourier representation here to have such a representation. In general, for any activation function, it is not easy always to find the representation, but we assume we have such a representation. And then we form a neural network ansatz, beta of x, which is given by k nodes. We sum from 1 to k, and we have the amplitudes beta hat k and the frequencies omega k, and the activation function sigma here that is related to the representation. For instance, it could be that. But I will use the real setting here, so that have to be like this. Okay. Now, how to find the amplitudes is given by this training problem. So you want to minimize the amplitudes beta hat given by the empirical sum of, and the loss function is the L2 here. So here, this is yj is this. And then we have the neural network function. And then we have two penalties. This is standard penalty, lambda 1, and the L2 norm of the amplitudes. And then we also will use amplitudes to the power here. 4. So what about the frequencies omega? In the random Fourier setting, then they are Fourier feature setting, they are independent samples from a density. And then one may ask, how should one choose such a density? That is a challenge, actually, to in practice find a good density P. But what one know, an optimal density. Suppose now that we have a sigmoid function or some activation function that is bounded, also the trigonometric is bounded, then an optimal density is related to the representation we had with the amplitudes. And that that actually minimizes the variance of the loss here, which we will soon see. But the question is, how can one find that? We don't know the amplitudes. Then one can obtain approximation of the optimal by using adaptive random feature approximation based on a kind of metropolis setting. And there are at least 2 posters on this by Kammonen and co-authors. And there is also a poster by Xin Huang on this, which I will mention in this talk. Okay, so here comes the theorem. So we assume that the representation with amplitudes has a bounded L1 norm in order to make sense of the problem, and that we sample with the density P, the frequencies, and that this quotient is bounded. So if we have a lot of high frequencies also in the optimal, then also the sampling need to have that in order to be bounded. So that is an assumption. And then we will look on what is the generalization error. So here is what we want to estimate: the difference between the function we seek and our neural network. And we are conditioning on the data points. So now we have a given neural network, given the data points, satisfy the training minimization. Then we take the expected value with respect to the data points X to evaluate how big is the loss, and expected value with respect to all frequencies that we have sampled from P. And finally, the expected value with respect to the data setting, so that we for instance, if there is a tiny probability that all data points come very close to each other, that will give a large error, but the expected value, in expected value, this has a small probability. So the expected value over all data settings with J data points, then we have a bound which depends on the number of nodes, 1 over K, and the number of data points, 1 over square root of J. When one chooses the penalty parameters for the L2 norm of the amplitudes, lambda 1, K divided by square root of J, and lambda 2, K squared divided by square root of 2. And this, the training, I can remind you, that is here, the training. It has 2 penalty parameters, lambda 1 and lambda 2. Is the setup clear now?
Yep.
Good. Okay, then here comes the plan for the talk. So the result in itself is well known in learning theory. For instance, in the book by Bach, Learning Theory from First Principles, you can find related results of generalization error for random features. So the idea here in my talk is to give a different proof that in some way doesn't use learning theory. It is totally simple-minded. Okay, and what is the idea? So we need a representation of the generalization error. And we need an estimate for the training error. And then we will apply Cauchy's inequality and the regularization terms. So in a way, the proof is related to ideas one use in inverse problems to get estimates for PD. Okay, so here comes the generalization representation. The left-hand side, this is the generalization error that we want to estimate. So we have the difference of the intended function and our neural network. We take the expected value with respect to data points and with respect to our frequency setting, and then the expected value with respect to the data set. And we split it up so that here we form instead of taking the expected value of the data points, we take the empirical mean here. The empirical mean, I go back to show you what that was. I forgot to say that precisely. So when we do the training, we form an empirical mean, and that I call E hat J. That is the empirical mean, summing over the loss here over the data points. This is something known. Yeah. Okay, so here we have the training error. And here we have the difference of the training error and the generalization error. So clearly we want the training error to be small, and then we will try to use the relation here to estimate the second term. The complication is that we don't have complete independence of things, so that it is not trivial to do this difference. That this difference is trivial if we will have independent samples, sum of independent variables, which we don't in this case. And I will show you how it works. So we look first on the setting with no noise. And the training error. Then we have assumed that we have a representation of the function. You can think of the Fourier representation. Then this is the Fourier transform, and if here we would have the Fourier exponential e to the I omega x would be here, and then integrate with respect to the frequencies. Now we make Monte Carlo approximation of this integral. Then we obtain this Monte Carlo approximation. We have omega k sampled from the distribution P. And I denote the amplitudes here, because we will use them later, by alpha hat k. And this neural network from the Monte Carlo approximation, which will be a kind of test function, we can think of as a test function that we cannot find it in practice computationally exactly, because we don't have these, but theoretically we have it, and we call it alpha. So it is a neural network like that, which has the property that if we take the expected value by construction of this neural network, the expected value of this neural network, we obtain the function itself by construction, because the P will cancel out when we integrate up over the omega density. Now, the training error can be related to the loss here. So the variance of this, we saw that there is no bias. So this is the variance with respect to the test neural network alpha. So I write it up what it is. We have a sum over 2 over k and over L from 1 to capital K. And here we have the difference 2 times. Now, since the frequencies omega are independent, when we have k different from L, the product cancels by taking the expected value. So only the square survives, and we have only one sum left, and 1 over k squared, and then sum over k, we can simplify to 1 over k, and here we obtain an estimate of the variance. So we have 1 over k and a function here that depends on the density we sample with, and the optimal density we could sample would minimize this variance, as I said, and that turns out to be, if this is bounded, say by a constant or bounded by 1, if it is the Fourier network, then we will have this optimal density that minimizes the variance. It is optimal in this sense that it minimizes the variance. I will show you later precisely how to obtain that, but it's given here. You just do a minimization with respect to the density. Okay, so we have assumed that that for this test neural network alpha, that the sampling density, here we have the optimal density divided by the sampling density, that this is bounded. That implies that that for the test neural network, the amplitude functions, they are bounded by 1 over k. And then if we plug that into, here is our training construction. We want to minimize with respect to the amplitudes in the neural network beta hat, this expression. This minimum will be less than if we plug in the test neural network alpha, so that we have here. And for the test neural network, we know that the L2 norm here, the amplitudes are 1 over k. So this sum here, this will be that, and this sum here will be that. And we just showed in the previous slide that the variance here is 1 over k. So the training error has this bound. Now, the representation for what we want to study is the generalization error. Then we split it up into the training error. So here is the empirical mean instead of the actual mean. This we have shown now is bounded, the training error. 1 over k, lambda 1 over k, plus lambda 2 over k squared. And what remains now to prove is that the difference here, using the difference of the empirical mean and the mean, that has a bound. And we will show now in a couple of slides that it has this bound. Okay, so that's the goal now, to study the difference between the mean and the empirical mean in this setting here. So here comes the same expression, difference between mean and empirical mean, and then the mean with respect to the frequencies and the data. So we write the square loss here. We write out it as beta squared minus 2 beta f and f squared. And I will study this term here now, the first term. The first term, we can write that this as a double sum here. We have a product beta squared, and then here is the same product. Okay, And the idea, so in the empirical mean, that only acts on x, and of course also the expected value acts on x, so that we can move this empiric difference acts here. Okay, so that's the first step in the proof idea, sort of. And then the next step, as I mentioned, is Cauchy's inequality. So now we have a double sum here and an integral with respect to omega. And we do Cauchy's inequality here with respect to that, and we obtain beta squared here and the sum. So this is the total integration, and then square root of everything. And then the other term, here is the total integration, and here is that term squared, what we have here squared, and the other here is this squared, and this is that squared. Okay, and then a square root for both of them. So that's Cauchy's inequality. And now we know the penalty was constructed so that to make this bounded. So the first term, this times that, we simplify to, we get the sum, this sum plus that sum by the arithmetic geometric mean inequality. So we have two terms, this one. First, that is direct from the estimate we have from the training error, because here we have the L2 norm to the power of 4, 2 times 1 here and then one other here with the sum over L. So that is handled by this term here. Lambda 2 times that is, if we have a control of this term, we know that this term is bounded by this. And that what remains is the other term. Here we have square and 1 over lambda downstairs now. This comes in the next slide here. So here is the square term, and then the integration with spread and sum over k and L and integration. Now we will use the expected value with respect to the data set. So that moves in here. And then we write out the square. What we have, the square is written out in detail here. The square is written out, the double sum, 1 over j and 1 over I. So here is the term with j, and then we have a term with I here. And I denote the expected value by EKL. They are, of course, the same here and here. Okay, so then again, now when we have this expected value, when I and j are different, the term, this kind of term will vanish, and the double sum will only be one sum, and we get 1 over j, and then the expected value here will be just this squared now. And that is bounded, and we obtain, because we have assumed the activation function to be bounded. It also, one can give a proof when the activation function is not assumed to be bounded. It's the same kind of proof, but the assumptions in the theorem is 1 or 2 lines more. So the total estimate we have is that we have k squared terms here and then 1 over j. So that error will be k squared divided by j. And the important thing we have been using here is that the data points xj and the frequencies, they are independent. So 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 here omega k does not depend on data points. This is used in that with this cancellation we obtain here. This is true for random features because omega, they are supposed to be sampled independently. But if we would do a standard minimization in the stochastic gradient, then the frequencies will not be independent of the data points, and this step will not hold. So this proof is restricted in some sense to random features. We cannot easily generalize it to neural network based on stochastic gradient descent. Because of this, we are using precisely independence here. Okay, so then, yeah, if we go back to the theorem, the statement, then we have now proved this statement in the setting where we have no noise. Yeah, and it was based on simple things. Yeah. So yeah, it is what it is. It uses that. Now let's see if we can do the noise case also. If we add a noise, then we have a second step here. Now the problem is now to estimate in some way in the training error, to estimate in the training error. That was the simple case before, but now with noise, we need to do some things with the training error. The other part with the generalization error, with the difference of the empirical mean and the mean with respect to x, that will be the same as we already did. But the noise we have to do something with the noise regarding to the training error. But when we studied the training error a couple of slides ago here, we estimated that by plugging in the test neural network alpha. We will do that again. And to simplify the calculations now, I just subtract a constant, namely the variance of the noise. So this is a constant we are subtracting. We are subtracting it here and here. It doesn't affect the minimization. We have a constant there. Okay, so this is what we want to estimate, and we replace the neural network with which is minimized. So we take the test function, which can only give a larger value. And that larger value, because the test function does not depend on the noise, then it simplifies to the thing we have already estimated, which is that. So we have one estimate of the training, namely it is that, but it is a bit complicated that it has a square here, including the noise, which we need to handle. Okay, so we do that by writing out the training here. We write it out with a square, this minus that. This is here. And then this times the difference is there. And this one squared is cancelled by what we have here. So here is what we want to study. And then we have an additional term here that pollutes our error estimate, and that need to be estimated. So we know that this is less than that, and then we have this pollution by the noise here. And then one can prove that this pollution here gives an additional term like similar to what we obtained before here with the generalization error, k squared divided by lambda 2j. We obtain an error where we use the penalty term lambda 1 and 1 over j. I will show you that in the next slide, but we still split it up into the training part and the generalization part. The generalization error, that works the same as before, as we did with no noise. It has not changed in some way. But what we need to do something with is this, to estimate that term, and that comes in the next slide. But given that we will obtain this estimate, then we have the same error as before, also with noise. So here comes this decoupling. Then here is beta, that is this function, and here is the noise, psi j. So this is what we want to estimate. And we will do the same as we did with Cauchy's inequality. So the empirical mean, we move inside, that the empirical mean hits on X here and on the data. Okay, and then we do Cauchy's inequality with respect to this summation here. So we get the amplitude squared, and square root. And then we have the empirical mean here, squared, and then the sum over the integration here, and then square root. So the first term, like before, arithmetic geometric mean, we obtain this. And the second term here, squared, we obtain that. 1 over lambda downstairs, and then the empirical mean here, squared, and the summation like that. So let us study this. This is under control. So let us study that. Comes in the next slide. So now we have to use the independence of the noise points and the data, and that the expected value of the noise is 0. So we have a sum here and the term squared, and then we move in we will use the expected value with respect to the noise. We will use that, so we move that in here, change the order of integration. Okay, and then the double sum here is written out explicitly here. So we have a sum over I and j. Here is j, and here is I. J and I. Okay, and when we take the expected value with respect to the noise here, that when I and j are different, then we get 0 because of the independence here, and 0 mean, so that only one of the sums survives. And then we have one sum from j equal to 1 to j and 1 over j squared. And we get, and from here we get k terms, and then 1 over lambda 1 and j, this j and this j gives 1j. And then we are left with the square here of the noise, which gives the variance s squared and some constant. And we have obtained the estimate we wanted, k over j. So that finishes the proof of this estimate here, that the training arrow satisfies that estimate, K over J. See, so we have some time left. In the beginning of the talk, I mentioned the optimal sampling density, and we saw the error estimate, the variance. Let me go back to the variance. Yeah, that the variance we have here, A squared sigma squared divided by P squared, and then when you take the integral over the density, you get only 1 power of P. That is what we have. That is what we have here. And then we need the integral over P to be 1. So we have a Lagrange multiplier here for that. If we want to optimize with respect to P, we get the variational problem here with any test function here. So you take the derivative with respect to P, you get 1 over P squared here, and the derivative with respect to P, you get 1, and then you have the test function. So the optimum need to satisfy that P squared is proportional to A squared, which gives the optimal then that P star omega is A omega divided by a L1. This is what we have here. Okay, so how can one in practice obtain that? That goes back to some work we did with Akko Kammonen and Peter Pleschak and Matthias Sandberg some years ago with adaptive random features, which includes a metropolis sampling. So we see that the optimal density has to do with the amplitudes A. And we don't have them, but what we have are the neural network amplitudes. So one could hope that one could sample something that approximates the optimal by using the computed amplitudes. And this is done in a poster by now in the conference we have by Huang and other authors in our group. So we tried to learn a molecular dynamics potential for a simplified 2D model. And then the optimal density in 2 dimensions, omega 1 and omega 2. The optimal density is here. And when it was trained with gradient descent, we obtained this empirical density using a metropolis test that I will describe. In this work, we used the adaptive metropolis, and here we used standard gradient descent. And you see, it's a bit surprising that the optimal density is not surprising that we have a potential that comes in the next slide. So it has a minimum in the center here, and the most dynamics is around the center. When it goes out, there is little probability to be here out. And here is the true two potential. Here is our approximated potential, and here is the difference of the potentials. So it's not surprising that it's optimal to sample much in the center because here are the paths very often. And but we were surprised that it had this fascinating structure that it is sort of oscillating here, and that both the gradient descent and the adaptive metropolis actually capture this oscillating behavior. It samples most in the center, and then outside it is not important to sample because there are very few paths going out there. Okay, so here is a quick description of what the adaptive random feature does based on metropolis. So when you do random feature, you obtain the amplitudes, and you want to do adaptive change of the frequencies. So you construct a random walk proposal step for the frequencies, and for these new frequencies you can compute the amplitudes again, and you have the new amplitudes. Okay, and then we apply a metropolis test with respect to the new amplitudes, and this test is given by taking the proposal amplitudes divided by the current amplitudes, and then a power gamma that I will explain shortly. It should be large, this. So that was what is used in the sampling here, adaptive metropolis. And what we have proved before, so yeah, okay, so you remember when I had a test neural network alpha, then the amplitudes for that, for the they were a omega k divided by k p omega k. So this and now the A here, if we take Fourier neural network, I call it F instead. So we have the Fourier transform. So these are the amplitudes from the test neural network. If we would assume that the computed amplitudes will be related to that, we can estimate the optimal in some way, but it's difficult. I mean, in general, it doesn't convert. This is solved by least squares. It doesn't have to be converted into this in some sense for a finite k. But what we have been able to analyze is that in the limit of taking infinitely many nodes, it converges weakly in this sense. So if you form some average over frequencies, then there is some convergence. Okay, so which motivates that we could use the computed amplitudes here, the computed amplitudes, to find the optimal. So if the computed would be actually the optimal, then the metropolis method will sample from the density p here, the density p, and that this would be optimal. And then to have a fixed point in this relation means that the density will be proportional to the frequencies function, I mean the Fourier transform of the frequencies to the power gamma 1 plus 1 over gamma. And that if gamma is large will almost sample from the optimal density. Okay, Here is algorithm how one do this adaptive metropolis that will be also given in the posters by Kammonen and others. So you are given input data, and you want to compute the Fourier neural network here. And you need some parameters, the sampling time, proposal step length in the random walk, and the exponent gamma I mentioned. And then one also, here are a little bit different penalty parameters. Instead of lambda, they are called delta hat here. And you'd want to have a number of time steps. So you start out with a 0 frequency, and then you compute neural network amplitudes, and you do a random walk here in the frequencies. You compute the proposal frequencies, now the proposal amplitudes, and then you check the metropolis test, and you iterate over that and obtain a neural network. So in the poster you will see variants of this. The poster by Kammonen improving and comparing by still using the idea of trying to sample the optimal density. Yeah, I think I finish here. So thank you.
Thank you very much. Thanks once again for this